This is section 7.3, and again we're talking about sampling distributions. We didn't quite finish it in our last section. We were talking about the sampling distribution for our sample mean. Okay, and so we know that our sample mean will vary from sample to sample, and thus the sample mean itself becomes a random variable because we don't know in advance what value we will get. And this random variable, the sample mean, now has its own distribution. It has its own mean, standard deviation, shape, etc. because it's for all the different possible values of the sample means I could get based on which sample I choose. Okay, so for example 7, unknown to an experimenter, the corrosion rate of a certain type of metal has a population standard deviation of 10.3. He decides to estimate the mean corrosion rate. He takes a sample of n equals 32. What is the probability that his estimate will be more than 2 away from the correct value? The first thing you need to know is, well, what is your distribution of x bar? They didn't tell us the shape of the original population, but they did tell us that our sample size is at least 30, which means that we are guaranteed to have a normal distribution. Also, the mean for x bar is always equal to the mean of the original distribution, and we don't know that, so we'll leave it as mu. And sigma for x bar is equal to the original standard deviation over the square root of n. So 10.3 over the square root of 32, so 1.82. The next thing we're going to do is actually try and set up our probability. So we're looking for the probability that his estimate is more than 2 away from the correct value, which means that the distance between x bar, his estimate, and the true value, mu, has to be greater than 2. So we set it up as an absolute value. Now I don't know how to find this. I only know how to find the probability that x bar is greater than or x bar is less than, etc. So I want to use some algebra and rearrange this. So I could rewrite it as the probability that x bar minus mu is less than negative 2, or x bar minus mu is greater than positive 2. I can rewrite this once again as the probability that x bar is less than mu minus 2, or x bar is greater than mu plus 2. Notice this is now the format that we're used to working with. Okay, we've done this for a couple different sections now. I know how to find the probability that x bar is less than something or x bar is greater than something. I need to standardize, and I need to do it using the mean and standard deviation for x bar. So it's going to be x bar minus the mean of x bar over the standard deviation of x bar less than mu minus 2, or x bar minus mu of x bar over the standard deviation for x bar is greater than mu plus 2. Sorry. I didn't actually standardize the values, did I? So the x bar value at the moment, I'm looking for the probability that it's less than mu minus 2. So it's mu minus 2, that quantity, minus the mean of x bar, which is mu, divided by the standard deviation of x bar, which at the moment is 1.82. Okay, or x bar minus mu of x bar over sigma of x bar is greater than, it's going to be mu plus 2 minus mu over 1.82. Because I've standardized, these are now the probabilities of z's. So this is z is less than negative 1.10, or z is greater than 1.10. If I was to draw my picture, so here's my negative 1.10, here's my 1.10, I'm looking for the area in each tail. When I look it up on the z table, I get that the area in the left tail is 0.1357, which means the area in the right tail is also 0.1357. So it's 0.1357 plus 0.1357 equals 0.2714. So let's think about what this means. This means He doesn't know what the true value is, but the probability that his estimate is more than 2 away from his correct value is only 27%. If he wanted to make that probability smaller and smaller, so if he wanted to ensure that his estimate is closer and closer to the true value, he could take a larger sample size. Okay, that was the last problem for sampling distributions for the mean. Now we're going to go on to sampling distributions for counts and proportions. So for sample counts, when we only have 2 possible observations or outcomes for a random variable, we summarize our results by giving the count for one of your possible outcomes. So like counting how many people say yes to if they prefer brand A of toothpaste, something like that. So n is our sample size, and x represents the random variable that gives our count for our outcome of interest. Now our sampling distribution of a count, we learned this before, but if our population contains a proportion p of success, as long as our population is large enough, so larger than the sample, then your count x of successes in a random sample without replacement of size n has approximately the binomial distribution with n and p. Now we know it's not exactly the binomial distribution because it is without replacement, so its probabilities of being chosen change just a little bit, but not enough to make a difference because our population is much bigger than our sample. Now, because it's binomial, we know the formula for the mean for a binomial is NP, and we know the formula for the standard deviation is the square root of the variance, so n times p times 1 minus p. So we know the mean and standard deviation for our count x. We can also use a sample proportion. So when a random variable has only 2 possible outcomes, we can also use the sample proportion as a summary of our data. So p hat is x over n, number of successes over the sample size. Before we find a sample, we don't know the proportion, so the sample proportion p hat, because it can change from sample to sample and we don't know in advance what it will be, that's what makes it a random variable. So x is the count, p hat is the proportion. They're both random variables, but they are 2 different statistics. However, if you know x, you can find p hat and vice versa. Okay, we have the mean and standard deviation of a sample proportion. So like let p hat be the sample proportion of success in our random sample, with a population proportion p of successes. Our mean for all of the possible values for p hat, because again p hat changes from sample to sample, so it's its own random variable. And so if I found all of the possible samples and all of the possible sample proportions, then I would have this data set, and I could find the mean and standard deviation of that data set. So that's what these are. So the mean for all the possible sample proportions is equal to p, the original population proportion, and sigma for p hat is the square root of p times 1 minus p over n. Okay. So example 8, suppose in the US 60% of college students are satisfied with their online clothes shopping experience. If you randomly sample 2,500 students, what is the mean and standard deviation of the sample proportion of students who are satisfied? So start with, what data did they give me? N equals 2,500, P equals 0.6. So the mean for all those possible sample proportions is equal to the original population proportion, which was 0.6. And the standard deviation for all those possible sample proportions is the square root of p times 1 minus p over n. So the square root of 0.6 times 0.4 over 2,500, which is 0.00979. Okay. Now you might have noticed that the standard deviation for p hat does require us to know the true population proportion. But if we're ever estimating our population proportion p with our sample proportion p hat, then we're not going to know the standard deviation either because we won't know that exact value of p. So what we can do is we can estimate the standard deviation of p hat, and now it becomes a standard error. So standard error just means the standard deviation of an estimate. So standard error is just another way to say the standard deviation of the estimate. And instead of p's, we'll put in p hats so that we can actually estimate our standard error. So for example, we want to estimate the proportion of U.S. college students who shop on Amazon. Suppose we take a sample of 150 students and find that 121 of them shop on Amazon. What is our estimate and the standard error of the estimate? So our estimate is our sample proportion, and in this case there were 121 people who said yes, 150 people in the sample, so it's 0.8066. That's the actual estimate, and then the standard error is SE of p hat, so we define it as p hat times 1 minus p hat over n. So 0.8066 times 1 minus 0.8066 divided by 150, n is only 150, which gives me 0.0322. Now in this class we've already talked about the normal approximation for counts. So we already knew that our normal distribution can be a good approximation for the binomial distribution. But I just wanted to remind you why. So here's an example of a binomial distribution that starts with a sample size of 6 and a population proportion of 0.3. Notice when it starts off that it's definitely right skewed, it looks very discrete. Okay. When I raise my sample size to 12, it looks more symmetric. The bars are a little bit closer together. At n equals 120, it's very symmetric, very normal shaped, and it looks more continuous. And by the time we get to 1200, it's definitely symmetric, and you could probably just work with it as a straight continuous distribution, and it wouldn't make a difference because those bars are so close together. So the normal distribution is a good approximation for the binomial distribution if our sample size is large enough. So if we have a simple random sample from a large population with a population proportion p of success and n is large enough, then the sampling distributions for x and p hat are approximately normal. And x is approximately normal with a mean of np, and I accidentally wrote the standard deviation instead of the variance. So standard deviation for x is the square root of np times 1 minus p. And the standard deviation for p hat, so p hat is approximately normal with a mean of p, and the standard deviation is the square root of p times 1 minus p over n. And we can use this approximation of n times p is at least 5 and n times 1 minus p is at least 5. Now, in most classes, in the lower level classes, we just teach this and students just standardize directly and go ahead and find the probabilities. But in this class, we have learned about the continuity correction, so we're going to get better results if we use that. Now, the continuity correction, we only have a built-in continuity correction for counts. Okay. If we don't have one for our proportions. So for every problem that asks you to find the probability for sample proportion, just switch it back to counts and find that probability so that you can use the continuity correction. Because you will get slightly more accurate results. So for our first example, let's suppose that in the US, 60% of college students are satisfied with their online clothes shopping experience. If you randomly sample 2,500 students, what is the probability that the sample proportion who are satisfied is at least 58%? So we are looking, let's write down what they told us. So our population proportion for all people is 0.6. Our sample size is 2,500. And we are looking for the probability that p hat is greater than 0.58, greater than or equal to 0.58. But we need to switch back to x's or our count so we can use the continuity correction. Well, if 58% of 2,500 students, to figure out how many successes you need, or the counts, you can just multiply. So 0.58 times 2,500. So really we're looking for the probability that x is greater than or equal to 1450. So now I'm looking for the probability that x is greater than or equal to 1450. Now it's going to be approximately according to the normal distribution. Okay. The probability that x minus np over the square root of np times 1 minus p. Okay, because it's x minus the mean of x over the standard deviation of x. It's going to be greater than or equal to. Well, we do need to use our continuity correction. Okay, now remember, for your continuity correction, you just add or subtract 0.5 in order to try and make your area bigger. So we're looking for the area to the right, so I would actually subtract 0.5 to make that region just a little bit bigger. So it's 1450 minus 0.5 minus my n times p. So this gives me the probability, because I standardized, so the probability that z is greater than or equal to negative 2.06. And I have to use the complement rule here when I look it up on the table, because the area to the left is 0.0197. So 1 minus that gives me that the area to the right is 0.9803. For our next example, we toss a fair coin 100 times. Find the probability that the number of heads is between 36 and 62. So here we have p equals 0.5, n equals 100. 0.5 because it's a fair coin. And we just do the exact same steps. So the probability that x is between 36 and 62. I'm reading it as include the endpoints. So we have to standardize both of these values now. First, let's figure out what my continuity correction would be. So here's my 36, here's my 62. I want to do a continuity correction for both of these numbers, and again for each one I want to make my region bigger. So I need to minus 0.5 for my 36, so it's going to be 35.5. This is only an approximate probability. Okay. And so 35.5 minus n times p, so 100 times p, over the square root of n times p times 1 minus p. So it was x minus np over the square root of np 1 minus p. Less than or equal to. Now for my 62, to make this region bigger, I need to add 0.5. So 62.5 minus 100 times 0.5 over the square root of 100 times 0.5 times 0.5. So this equals the probability that z is between negative 2.9 and 2.5. So to do this, I'll look up my 2.5 on my standard normal table, that's the capital P, and then I'll look up negative 2.9 and subtract the two numbers. So 0.9938 minus 0.0019 gives me 0.9919. So for the next one, find the probability that our sample proportion of heads is 0.53 or higher. So the probability that p hat is greater than or equal to 0.53 equals the probability that x is greater than or equal to 0.53 times 100. So I need to switch from proportions back to counts, so I can use the continuity correction. So the probability that x is greater than or equal to 53. And I need to standardize this now. First, let's figure out what my continuity correction should be. So if I'm looking for the probability that it's greater than 53, I need to subtract 0.5 to make that region bigger. So x minus np over the square root of np times 1 minus p is greater than or equal to my, let's see, 52.5 minus n times p is 50 divided by the square root of 100 times 0.5 times 0.5, which gives me the probability that z is greater than or equal to 0.5, and you use the complement rule. So 1 minus 0.6915 gives me 0.3085. So there's about a 30% chance that my sample proportion is going to be 0.53 or higher. So we skipped 13 because I felt like we've had enough practice, but if you want to check your work, just a few things quickly. P equals 0.68, n equals 1000. We're looking for the probability that p hat is less than 0.6, probability that x is less than 600. So I'm skipping the work so you can check your results. The probability that z is less than negative 5.34, which is approximately 0. And finally, example 14, we toss a biased coin 150 times and get 37 heads. We want to estimate the true probability of heads for this coin. What is the estimate and the standard error of the estimate? So this is just going back to the previous page. Our estimate, well, a good estimate for the population proportion of heads, or a true probability of heads for this coin, would be p hat, and for this coin that would be my 37 out of 150, so 0.2466. Notice this is a biased coin. I have no idea what the true probability of heads is, but right now my best guess is that the true probability of heads is about 0.2466. And the standard error, SE of p hat, is defined as the square root of p hat times 1 minus p hat over n. So the square root of 0.2466 times 1 minus 0.2466 over 150. And this gives me 0.0351. Last page. So this is just a few more interesting sampling distributions. So the first one is the sampling distribution of our sample variance. So x1 up to xn are our observations for sample from a normal population with a mean mu and a variance sigma squared. Then the sample variance s squared has this distribution. So if you take s squared, times it by n minus 1, and divide by chi squared, you'll get, divide by the variance squared of the population, you will get a chi-square distribution with n minus 1 degrees of freedom. We're not going to use that yet, okay? But it's an interesting result. Okay, this next result is the one that we will use very soon. So our sampling distribution of x bar when we don't know sigma squared. So we learned that we can estimate the population mean mu with the sample mean x bar, and that the standard deviation of x bar is sigma x bar equals the original population standard deviation over the square root of n. However, if you need to estimate the population mean mu, you're not going to know the population mean standard deviation either, or at least that would be very unlikely. Okay. And so instead of using sigma in our calculations, we need to estimate sigma, there is sigma, with the sample standard deviation s. But as soon as we do that, we switch from using the standard normal distribution to using the t distribution. We talked about the t distribution once before. And so what happens is if x1 through xn are observations for our sample from a normal population with mean mu and unknown population variance, okay, then the sample mean, once you standardize it, it has a t distribution with n minus 1 degrees of freedom. And you're going to standardize it by x minus the population mean over the sample standard deviation over the square root of n. Okay, this is exact if we have a normal population. And it is approximate if n is big enough, and the rule of thumb is if n is at least 30. Now in this case, we'll estimate our population mean mu with our sample mean x bar, and the standard error of our estimate, so just remember it's our standard deviation for our estimate, is defined as s over the square root of n. So we're using an s now instead of our population standard deviation. So just as an example, we did this problem in class earlier, so we wanted to estimate the mean height of a student in this class. We're going to draw a sample x1, x2, up to xn of heights of students in this class. So our sample size was 6. Okay, so first of all, what is the population? The population was all 29 students in this class. And we don't know the population mean or the population variance because we're not going to get the data for everyone in the class. But our data for just the 6 people is 76, 78, 66, 72, 69, and 65. So this is in inches. What is our estimate of the population mean height? Well, to do that we need to find x bar. So 76 plus 78 plus 66 plus 72 plus 69 plus 65 divided by 6 gives me 71. So our best estimate of the population mean height is that it would be 71 inches, basically 5 feet 11 inches. Now, what is the standard error of our estimate? Okay, if I put this into statistical software, I can find the original the standard deviation of my sample is 5.29. That's my best guess for the original population standard deviation. And so then if I want to find the standard error for x bar, it's s over the square root of n. So 5.29 over the square root of 6 gives me 2.1596.